Hello everyone and welcome to this session. So today we're going to talk about data sharing between processes in 4D, and we'll be focusing on this new approach that is available in 4D since version 17R4, that is shared objects and collections. My name is Omar Debbagh and I'm a project manager in the professional services team in 4D Morocco. So here are the topics that we will mainly talk about in this session. First of all, we're gonna see why a new approach to data sharing between processes. What is the need behind this new approach? Here we'll also do a comparison with the interprocess variables approach. Then we're gonna talk about how we can handle these shared objects and collections. We'll also see an interesting concept of shared groups, and we're also gonna talk about some points to watch out for when using these new objects and collections. Then we're gonna see some specific shared objects that are storage and signals. And at the end, we're just gonna try and do a little example where we can try and gather around everything that we're gonna see in this session. So, why a new approach? Actually, in 4D and since always, in order to share data between processes, we use interprocess variables approach. It is a fairly simple approach, but has some drawbacks. The first one being the fact that, well, interprocess variables are not compatible with preemptive mode of execution. As a reminder, preemptive mode is a very powerful feature that allows us to have better performances when executing our processes in multi-threading. So in order to see what actually this preemptive mode brings, we're gonna do a little comparison between the two modes of execution of processes in 4D that are cooperative mode and preemptive mode. So when we execute our processes in cooperative mode, what happens is all of these processes are dedicated and executed on the same CPU. That means that even if we run our database in in a very powerful machine with multiple core, what's gonna happen is that suppose that we launch two processes at the same time. So what 4D is going to do is that it's gonna launch the first process to execute till this process execute the command idle, either explicitly or implicitly. Explicitly by calling it in the method in the code, or implicitly by executing and running some code that actually calls this command internally. So when that happens, 4D looks for other processes to execute. When it finds the second process, it launches the same way till this process itself finds the command idle to yield back the hand to the process number one to continue executing, and we keep going that way until all processes are being executed. On the other hand, with the preemptive mode, what happens is that 4D gives the hand to the OS to execute our processes. So what the scheduler does is that it assigns every single process, process to a single CPU. So we get something like this. If we launch two processes at the same time, so the OS assigns the first process to a first CPU and the second process to a second CPU. And by comparing these two schemas, we can already see that well, the difference is huge between the two modes, because in the preemptive mode we have a very short time of execution, and it allows us to have better performances on our application, especially when we are running multiple processes at the same time within a powerful machine with multiple CPUs. However, in order to get the preemptive mode of execution, we have to meet some prerequisites. The first one is that our database should be compiled. Then we should actually tell 4D that we want to execute this method in a process that is preemptive. So what we do is we go to the properties of that method and check the checkbox that says that I want to execute this method in preemptive mode, like you can see here. The third prerequisite is that our methods should be what we call thread safe. Actually, when 4D gives the hand to the OS to execute our processes, what happens is we cannot call external commands anymore. So from that process, we cannot call like plugins commands or SQL database, etc. And we cannot use interprocess variables. And this is all it's about in this part, because with shared processes, shared objects and collections, first of all of its commands are thread safe, so they can be executed in a preemptive process, and they allow us to share data between our different processes, either cooperative or especially preemptive processes. Just a reminder here, if you want to know if a command is thread safe or not, you just gotta check the documentation of this command. If you find this specific icon, then that means that this command is actually thread safe and we can use it in preemptive modes. And if not, so that means that we cannot use this command in preemptive methods that we want to execute in preemptive processes. So that was the first big point that these new objects and collections allow us to do. The second point, and it's a very important point, is managing concurrent access. Actually, when you are using your interprocess variables, well, there is no automatic management of concurrent access. What I mean here is, for example, if you have defined an interprocess array that you modify in multiple places in your application, well, when a process A is modifying this value, nothing guarantees, at least automatically, that no other process is modifying this value at the same time. And this could cause some problems in your application, especially in terms of the integrity of your data. So what we use generally to remediate to this problem is semaphores. So we use and we write some code like this. We put our semaphore to protect the code that modifies, for example, our interprocess variable array, and at the end we clear that semaphore so we can so other processes can come and modify that specific object or execute that code that is protected. The problem here with this implementation is that first of all, if for any reason we forget to clear that semaphore, well, that could cause many problems in our application. So what's gonna happen is that the first process will execute that code, that semaphore will never be cleared, so that means that every single process that's gonna come to acquire this resource and modify on this resource will be blocked, and that could cause various problems in our database and various blocks in various parts on our database. The second point is actually when we are waiting for our semaphore to clear, what happens is we use some code like this. So we put this check in a while loop, and with every iteration we check if the semaphore has been cleared or not. The thing here is that, well, since we're using this while loop, our process is executing and it is consuming CPU time. Of course, here we can put some timeout, like 1 or 2 seconds, to prevent this point from happening. But again, it's the same principle. Nothing forces us to put this. Nothing forces us to put this timeout, and our process could still be running, and so as multiple process in behind. The way that these shared objects and collections deal with this is, first of all, concerning the problem of freeing that semaphore. What we do generally is that we initialize we define our new object, new shared object, and when we want access to this new shared object or to this new resource to modify on this new shared object, we are supposed to put the use and use block. When we put the use, what 4D does actually is that it puts an internal semaphore that blocks every incoming process when this current process is modified on this value. And by putting the end use at the end of our treatment, we free this internal semaphore that 4D put for us. So the thing here is that 4D, if we forget to put the end use to free that semaphore, well, we get first of all a warning in our code method, and then we get a compilation error. So we can't compile our database then. So that way we make sure that we're not going to cause some problems and block other parts of our application. The second point is when a process comes to this point and wanna require this resource to work with it and to modify its value. If this resource is used in another process, well, unlike the use of simple semaphores, what happens here is that we are our process is in a waiting mode and we're not consuming CPU time. It is really waiting for in a statue waiting for events. So that of course could be interesting in terms of performance. So now that we have seen why why we have this new approach of new shared objects and collections, let's see how we can manipulate and work with this new object. So, like we saw in the previous slide, we can first of all define our object with the, of course, command C object because it's still an object. Then we instantiate this object with the command new shared object. So at this point, 4D knows that this is a shared object and it's not a traditional object. Once we have this new object, we want to pass it, we want to share it to another process. So what happens is we should put this object as an argument to the command new process or new worker, for example. The difference here between traditional objects and shared objects is that with traditional object, we take a copy of this object and we pass it to this new process. Whereas with this shared objects, we pass only the reference of that object. So in this new process, new method, what happens is we have the reference to this object, so we can modify directly in the same object. So we keep at the same time the same instance of that object. We only have references to that object. Then in our new process, we can modify, if we want to access to write on this object to modify an attribute of that object. Well, what we should do is we should put our code between the use and use block. So we say, hey, I want to use this new shared object. So every other process should wait till I'm done with it, then they can work on it. So I do that. I modify an attribute, a value of an attribute of my object. Then I free the internet semaphore with the end use line. Then if we just want to read a value of an attribute of the object, we can just call it the classic way object that attribute, and we're gonna get the value of this attribute. So we talked about passing the reference of an object to another process. Some of you may say, because we're talking about references, if we at a certain point of our application we have no reference left to that object, what happens? Do we have a memory leak? Actually, here I'm just gonna remind you of a principle that is implemented in 4D, in which at the time where 4D creates a new object, this object by default comes with an internal counter. So what happens is, the first time that we have a first reference to that object, this counter increments by 1. The second time means that this counter increments by 1. Also, if we at a certain point delete a reference, we get a -1 in this counter. And if we have no reference left to that object, when the counter passes to 0. So what 4D does is, when an object counter passes to 0, it self-destructs itself, and that way we have no memory leak. And this is 4D's way to implement this garbage collector that we have in other programming languages. So here we're gonna talk about two points to watch out for when using your shared objects and collections. The first one is what we call bottleneck. Actually, when you use a certain object, when you want to modify the attributes on a certain object, suppose that you have to do some treatments or have your user write a value to get, then put this value in your in an attribute of your shared object. What you shouldn't do is, well, put this treatment or inside the use and use block. That is not the right way to do it. What you should do is get your treatment first, get your result, and then inside your use and use block, when you require your resource, your shared object, have the most minimal code possible. In that case, just to set the value of an attribute with the result. No treatment there, no interaction with the user, because if you do so, what's gonna happen is that it's gonna block all the processes that are coming and wanna use this shared object. So you should look out for this. You shouldn't do it the first way. You should do it the second way. Another thing to watch out for is what we call deadlocks. Actually, what deadlocks are, deadlocks can happen when you have, for example, two processes, and in these two processes you have two shared resources in the two processes. So process number one already uses resource number one. Process number two already uses resource number two. And in your process number one, you're trying to access to resource number two, and in process number two, you're trying to access to resource number one. If that case happen, well, it's gonna block both your processes, and it could block your application. So you should really watch out for that point. You can each time that you have more than one resource that is required in a process, it is a potential problem, and it could cause deadlock, so you should watch out for this so that this case doesn't happen in your application. So we could imagine something like this in 4D. You got two resources, two shared objects that you pass to two different processes, and in process number one, we already use resource number one and one access to resource number two, and in process number two, we already access to resource number two and one access to resource number one. If that happens at the same time, that could completely block your application, so watch out for this. So now we're going to talk about a very important concept, that is shared groups, and this concept actually is related to what we call a lock-in identifier. Actually, in all new shared object, all this new shared object, once we have defined a new shared object, this object comes by default with an attribute that is his lock-in identifier. By default, this lock-in identifier is negative, which means that it is simple, but then it could be positive, and that means that the object is not negative, it is now positive, and it is part of a shared group. To understand this concept, I have here, for example, let's take the example that we have three shared objects. Each shared object has its own lock-in identifier. So here we got object A with -15, object B with -16, and object C with -17 as their lock-in identifier. If at a certain point we decide to put object B as an attribute of object A, so what happens here is that object B and A loses both the negative lock-in identifier, and they both get the same lock-in identifier, which is the positive value of the parent object. So here the parent object is A, it had -15 as its lock-in identifier, so now it passes to +15 for both objects, and they both form now what we call a shared group. The same way, if we want to put a simple object in a shared group, we can do it the same way. We put C, for example, as an attribute in our object B, and what happens is object C loses its negative lock-in identifier, and it gets the positive lock-in identifier of the shared group, which is +15. So what that means is, if we at a certain time, now we have this shared group with this lock-in identifier. If we want access to, if we do something like in process A, if we do something like use object A, now we are locking not only the object A, the object A, but also object B and C. So if at the same time at another process we do something like use A dot B, that we will not access to this process, because all to this object, because all of them three objects have the same lock-in identifier, and they are going to be blocked until the treatment of process A is done and the internal semaphore is freed. So if then we decide to remove object B from object A, that doesn't mean that object B and object A are going to be simple. No, they continue to form our shared object. So the same way, if we want to remove object C from object B, the three shared objects, once they form a shared group, they cannot get back to be a simple shared object. So they keep their positive lock-in identifier. The same way here, if we wanna put object B and C at the same level and not nest B and C, B and A and C and B, we're just gonna get the same result. They're gonna form our shared group with the positive value of the locking identifier of the parent object, and the three objects are gonna form a shared group with the same locking identifier. But what we cannot do in 4D is put a shared group inside of a simple object. If you try and do this, you're gonna get an error from 4D and you won't be able to put this group, this positive locking identifier inside of a simple shared object with a negative locking identifier. What we cannot do also is put a group with its locking identifier in another group with a different locking identifier. So suppose that object C is part of an object of a shared group that has plus 16 as a locking identifier, and object and shared group A has a locking identifier 15. If we try and put object C in object B, for example, or A, we cannot do this because the two locking identifiers are positive, and we cannot put a shared group A in a shared group B unless they have, of course, the same locking identifier. If they have the same locking identifier, positive 15 for C and A, we can put C in A, of course. So now we're gonna talk about two specific shared objects that are storage and signals. First of all, we're gonna start with storage. What is a storage? Actually, a storage is, of course, a shared object, but it's a special shared object whose reference is known at all time. That means that in every part of your application, you can get the reference to the storage, and you could call it. It's somehow the same thing with the interprocess variable. You can call them from everywhere. So was the storage, but you only get the reference to the storage, so you can work on this storage. Then the storage is a catalog of references of shared objects and collections. What that means is that inside of this storage we keep references to another shared object. So we define a shared object that we put inside the storage. So by getting the reference of that storage everywhere inside your application, you can get, of course, the reference of the objects that are part of that storage. I should remind you here that a storage is, we have an instance of the storage inside the client, inside a client session, or inside a server also if we are in client server mode. So that means that the storage in your client session is not the same as the storage in your server side. So the two storages are different, and we cannot get values from storage in your client session in your server. And also, if your database is using components, each component will have its own instance of storage, and it's going to be different than the other ones. Like we said, storage is a very special type of shared object. So what that means that there is some rules that apply to shared objects that also apply to the storage, but there are some other rules that doesn't apply to the storage. We're gonna see this here, and we're gonna see why. First thing is, storage only accepts shared objects and collections. We cannot put a simple type in objects. We cannot put a string, a long integer or something else. We can only put shared objects and collections inside the storage. Of course, like traditional shared objects and collections, we in order to access storage, in order to write in a storage, we have to put it between the use and use block. The storage doesn't share its locking identifier. Excuse me. So this concept of shared group doesn't apply to the storage, because otherwise that would be problematic. Because suppose that we have now a storage with a locking identifier minus 15, for example, and we put in this storage two shared objects. Shared object A with its own locking identifier, and shared object B also with its own locking identifier. If we apply the shared group here, that means that the three objects will have the same locking identifier and are going to be like, so each time in which we're gonna use the storage, that means that we're gonna block all the objects inside the storage. All the catalog of objects that are inside the storage are going to be blocked, which is not practical. So what we do is storage has its own positive locking identifier, where and each and every object in the storage has its own locking identifier. And of course, at the end, if we locked an object of the first level of a storage, this one is locked. It's gonna be locked for other processes, but not other objects in the storage or the storage itself. So, for example, here we can do something like this. We do the use storage to write in our storage, and here we create our first object and second object in the storage, and they are like we said, shared objects. So you can see that the three objects have different locking identifier. So for storage it's minus 42. For the first object is minus 50. For the second object is minus 51. And here you can see that even if we put a shared object inside of storage, it doesn't share the same locking identifier. The second thing is, if we wanna use only if we wanna use only an object of that storage, then we shouldn't do something like use storage then use storage that something. No, because here we're gonna block the access to the storage itself in writing mode. So we can directly do use storage that something, and this way we can access to that object and modify an attribute of that object. Of course, in the same way as classic shared objects, we can access in reading mode a shared object directly without having to put the use and use block in there. Okay, so storage is good. It's very practical, but you should use it very wisely. Why? Because the use of the storage can be costly. So what you shouldn't do is put on your storage data that is temporary. For example, suppose that you define a new shared object that you put in your storage. You use inside your application this new object. Then at a certain moment, you remove this object from the storage. So that means that this object, the shared object, was temporary, and you shouldn't have done it that way. So here you could have just used the normal shared objects, create a shared object, then share it to that process that is going to need this new object and work that way. And you should minimize access to the storage, to your data that is persistent and that you are going to be always needing in your application, and not your data that is just temporary and that is going to be deleted then. Okay, so now we pass to see the signals. What are signals? Again, signals are specific and special shared objects that has integrated method and properties. The principal role of signals is to ensure the scheduling of processes. In order to understand this, we're just gonna do a little example here. Suppose that we have a first process where we define our signal. Of course, we're gonna define our signal with the command C object because it's still an object. Then in order to instantiate our signal, we use the command new signal. So when we do that, what happens is our object signal is created with of course, because it's a shared object with its locking identifier and with a special property that is signal, that is by default that has by default false as a value. So what we do here is if we wanna pass this signal, the shared object that is the signal, to a new process, we pass it like we saw earlier in arguments of this command new process or new worker, for example. So what happens here, we get our signal, so we get a second reference to this shared object, and then we use the function member wait. So what this does is that when process 1 is executing, when it reaches this point, it checks if the property signaled of our signal is true. If not, when it waits and till this property is switched to true. So this allows us to schedule our processes. Here typically we say that we do not want to continue executing our code until process 2 has been done executed, and we will see what is the code inside our second method, our second process. So just a reminder here, when we are waiting for this signaled property to pass to true, you see here that our process is flagged as waiting for internal flag, and it is not consuming CPU time. Again, it is good for performances. So in process number 2, we do our treatment, or we launch a dialog, for example, to get a value from the user. Then we create an attribute result in our shared object signal, in our signal. So what happens is we want to return this result inside of our shared object signal. So here we don't need to pass another shared object, because signal itself is a shared object. So we can add here this property that gets, for example, the value 1500, and then we execute the member function trigger. So what this trigger does, it actually triggers your signal and says to 4D, well, the signal has done its job, now you can continue executing process number 1. So here, when waiting at the time when signal passes the true, we do not have to wait anymore, and the process number 1 continue executing, and of course we can get and read the value that is returned from process number 2 and use it in what is left in our process number 1. So here we have reached the end of this session. What we are going to do here is just we're gonna see a small example where we're gonna try and gather around all what we have seen in this session. So for our example, let's just imagine something like this. Suppose that we have a validation process. It could be anything. Let's suppose there is a file validation process, a file for some user. So suppose that this validation process has or passes by three paths. First path being an eligibility verification, for example, eligibility of that user, then conformity of data that is in that file, and suppose that we do some calculation at the end. And let's suppose that we cannot validate this file only if all these 3 steps are confirmed. So what we do here, we could use all what we have seen in this in this session. So just gonna launch my 4D here. Okay, so just get back here. What we could do in order to make this process faster, so instead of doing everything that we just said in one single process, we could make this three separate process that executes separately. And of course, if we are in preemptive mode, then we can have the benefit of what we saw earlier with the preemptive process execution. So we're gonna see a small implementation of that. So first of all, what I do in this demo database is inside the onStartup database method is that I fill my storage actually. So in my case, I have here in my resources folder, I have a file that I named init.data, for example, and here, well, I just put information about APIs that I could use in my database. Sorry. So, for example, here we have URL, login, password. These are data that is persistent and that I could use in my application. So, I could put this data inside the storage. What you shouldn't put is inside the storage is data that is not persistent, that is only temporary. So what I do is I do of course the use, in order to write in my storage. So I do use storage. Then I define my new shared collection inside my storage. Then I come here to get the values of what I have in the file, to parse my file to get the objects and put them in my collection. So here I get my file, I parse it to get my objects, and what I do here is I transform these objects to shared objects in order to be able to push them inside my shared collection. As you know, we cannot put classic objects in shared objects. We cannot do that with 4D. And right now, we cannot also transform a shared object or a classic object into a shared object. That is not something that we can do with 4D right now. But you could, of course, do some code to write some code to do this. It's not really hard. And of course, you can do like me. You can just get here inside the knowledge database. This technical note here, you've got two methods. You've got the source code for two methods that are copy object copy to shared object, and object and the collection ob copy to shared collection. So what I use here is the method ob copy to shared object. I just pass here my classic object, and I get here my shared object that I push inside my collection. So that way I could get back the URLs, the APIs that I will need later in my application. So I'm just gonna execute this to get. So here, if we take a look to the storage, we're gonna see here that we have the three objects that we had in our file that have been implemented into our storage. So what I do here in order to implement this, what I do here, like you see, I have three processes: process 1, 2, and 3, eligibility, conformity, then calculations. So I'm going to use the signals in order to share data between these processes to get back the results from each and every process, and of course at the same time schedule these processes in the manner that we won't be able to execute past this line unless these three processes are fully executed. And this is just an example of the implementation, so you feel free to do like you want then. So what I do here is inside my signal that I defined here, I create my shared collection results. So inside this shared, what I do with this shared collection is that every time I get the result of each process that I put here, the result of of every process from these three processes will be just two attributes. First attribute is gonna define the status, will be just true or false. So the verification is okay or not. And a second attribute that's just gonna be a collection with messages that in case of an error says what is the type of the error, or in case of the validation is just gonna be something like okay. So what I do in order to schedule these three processes, like we said, is at the end of every process, what I do here is, of course, here the collection, I didn't put any elements in the collection, so the length of this collection is 0. So what I do here is, at the end of each process, I check if the length of this collection is 3. So that means that the only processes that are going to modify or to work on this signal will be these three processes right here. So if any process reaches the end and finds that the length of this collection is 3, so that means that it is the last process to execute. So that way we can trigger our signal and we can continue processing. So I'll just execute my method here. Before that, I just explained to you something, what I do in each method. So in this first method, I just get back my signal here. Here I use the storage, so I get back, sorry. So I get back the API that I need. Here I just apply this member function to get back the eligibility API. So I get that here. I pass this to this HTTP request method. What this method does, it doesn't really do a call to HTTP, it does just simulate this. So I just create here a message that is potentially returned from the API, which says here that there's a problem, you cannot benefit from this. So the status here is false. I just construct here my shared object result and with the status that is false and the message that I put in my collection, which is a shared collection. So I get this in here. Yeah, and so I get back here. I'll just show you what I have in my conformity process and my calculation process. So in my conformity process, I just construct my result, my signal.result collection. I push my result here and do the same check. I construct my results here and do the same check in order to schedule our processes, and I do the same thing here with the calculation part. I'm just gonna go ahead and execute this. So what we have here is our signal. Okay, with our shared collection results. I'm just gonna start with the first process I have here. So here, like I said, I get back my API that I passed to this method, and you're just going to see that here I push my object before actually constructing that object, before putting any value to that object. And this is an important point because if we compare with classic objects, usually what we do is well, we create our object, we construct our object, then at the end we push this object into a collection, for example. In this case we cannot do this because what I do here when constructing my object is that I put already a shared collection into a shared object, so that forms a group, a shared group. And like we said, we cannot put a shared group into another shared group or a simple shared object. So just be aware of that point. When you wanna use some code like this, you push your object first, and then and only then you construct your object and work with it. So here what we're gonna have here, if I get back my signal, my collection, now you see it is my result is empty. So here I come and I I do this. Now I have gotten back my value. Now if that line 15 was to be here, that would have raised an error in 4D, and we wouldn't be able to continue. So now like you see, we are still in the first process. So here the check, the length of our share of our signal, of our shared collection in our signal, is still 1. So this is the first process that executes, and of course it will not trigger our signal. So here we pass to our second process in the same fashion. If we get here our signal, we go in, we have a length of 2, and we aren't done yet. And here you look that we have the results of each process. The same way happens here. So at this point you see that our property signal have been put to true. So now we have our signal have been triggered, and we can complete our process here. So I do something simple here. I just do an alert, and we see what has been returned from each and every process. Just something, that shared collections, at the end of the day, they are still collections. So we can apply member function to this shared collections. We can do something like to get back our messages. Something like we can apply the function member extract to get back our messages. Then join to just get a carriage return right there. So we just alert our message, and you see here that I get back all the resultant messages from these different process. So that was all for this session about shared objects and collections in 4D. Thank you for watching, and I hope you enjoyed it.